a good way to take care of that. And then for this lab report, no calculations that need to be done. It's all just been taking our measurements, and then we're going to talk about it in the discussion. So the weighting that usually goes to calculations has been split up into the data lines section and your discussion section. So you don't need a calculation section, but you definitely need your data lines or data or experimental values, whatever you want to call it, and your discussion section. Data lines now out of 2, discussions out of 5, so that's half your grade right there in discussion in this lab report. The discussions are the most important part of this. For background, because there's no calculations, there's no really formulas or derivations that you need. So background can be pretty light this time. Really just use it as a bit of an introduction to the theory and stuff that you're going to talk about in your discussion. You don't need to go in depth at all for the background, but basic stuff like what solar panels are, quick on how they work, those sorts of things. You'll probably want to do a bit of research for your discussion questions. They are floating around out there. They can be a little hard to find. So there are manuals for these guys that basically describe them, tell you how they're built. You can always cite your lab manual. If you can't find the user guide or the user manual for the ISATs, there are research papers out there, mostly that just talk about how great ISATs are as a learning tool. But they include sometimes snippets from the manual or data cited from the manual, so you can use those reports as a good source as well. Try and make sure that they're using the same type of ISAT as there are, for example, newer models, and then there's also some really janky older models. If you see pictures of them online, they look really like they were put together by a bunch of students in a lab.
Do you know the model we have specifically?
The model we have specifically is either 3 or 4. If you're looking at a report or a manual for it, usually there'll be a picture of it in there. So that's always a good way to tell. If it looks somewhat like this, then you're probably good. If it looks like that, it's too new. If it looks like something I made in my garage, it's too old. So we have our groups. For apparatus, I have a list of all the stuff I expect to see in the lab report. So basically, you would just want a list of all this stuff. You'll then want pictures of all of it. You don't really need to describe what each thing is. That's what the picture there is for. So basically just a list, and then a quick sentence saying the apparatus can be found in figures blank through blank is good as well. For procedure, again, we can just cite the lab manual. We'll pretend that there were no deviations really. Everything was either just because something wasn't working, or we had to shorten it for time and use the lab video. In theory, we should have followed it exactly. You don't need to worry about deviations. So as we get into the data, all the data that we took down today will need to be in there. As well, you will need to watch the lab video for procedure 2 and 3, or procedure steps 2 and 3, and take down the data that they give in the video. In the video, they don't give data, every data point that's asked for in the manual, in the procedure. So just try and get as much as you can, everything they say. I'm very aware of the fact that the video does not do a good job for those steps. So just try your best and don't worry too much about it. But everything we did in here will be in your data line section. So then we move on to discussion. The first discussion question is going to be from the lab video. So you'll definitely need to watch that for this discussion question as well. And it just says, to discuss any conclusions you can make about the condition of the batteries. So when it talks about condition, it's really talking about where in the charge cycle of the batteries we're at. For that, we can look at this first chart here. The batteries that the ISAT uses are nickel metal hydride batteries. They're each 7 cells, which add up to make 8.4 volts nominal for the satellite. So that's our nominal voltage. And for these types of batteries, how they charge is they don't charge and discharge linearly, but rather they'll fairly quickly. For these guys, it's around 20% of their charge capacity. they'll rapidly charge up to their nominal value of 8.4 volts. And then for the majority of the charge capacity, you're going to get that nominal value. So from about 20% to 95% of the charge capacity, you'll be at that value. And then what actually happens is the batteries become a little bit overcharged, and then the voltage is actually going to start dropping again. And that is actually how a charger knows when to stop charging a battery, is it detects that the voltage is dropping again. So it stops charging it so it doesn't fry your battery and overcharge it too much. So for this question, you'll probably want to do a bit of research on these sorts of batteries, find a really nice chart of this, and then just talk about in the lab video where you think the batteries that they were testing were in this charge cycle. They tested 2 batteries, so probably answer for both of them. They'll have very different results, the 2 batteries. It's actually really good at illustrating the different spots of the charge cycle. For question 2, it says to discuss the voltage provided by the solar array, where in the range were these voltages, why, how did the voltage provided by the 2 solar arrays compare to each other? So where in the range were these voltages? To talk about what the voltages were for the solar panels and what they are on their own, what they are together. More than the 8.4 volts together, is it less? Why would it be more? Why would it be less? Those sorts of things. You're also going to be comparing the 2 solar panels to each other here. So for that, you can kind of talk about why one solar panel gave more than the other. We all notice that one would always have a higher voltage. So for that, you can talk about things like the age of these cells. These are all about 10 years old, a little bit older. Solar panels degrade over time. So maybe one's degraded a bit worse, maybe one's a little bit broken, maybe one was just never connected very well to begin with. There could be smudges or dust on one of them, or a scratch, things like that. You can also talk if there was equal light going to both of them, or if one solar panel always was receiving a bit of extra light, maybe from an external source, which would be a bit of an error in the lab. So that's discussion 2. For discussion 3, it says how did the voltage generated by the solar arrays differ when illuminated by the 3 different sources of light? Why was it different? And was the voltage measurement the same after 3 seconds and 1 minute, and why? So now here we're comparing the different sources of light. So some good things to think about are the brightness of the light, the wavelength of that light source, and maybe how that compares to the ideal wavelength for solar panels. You can also talk about the distance from the light source to the solar panels. You can talk about the angle of the light shining on the solar panel. So is it best when the light's hitting directly on the solar panel? Is it better when it's on an angle? That kind of thing. You can also talk about the beam conditions. And what I mean by that is for the LED flashlight, we consider that to be a point source. So we consider the light to be coming from a point and just radiating out. Whereas for the halogen lamp, that's more of a beam source. So we consider that mostly as light all traveling in a beam. And then the ambient lighting, we have light coming from all directions. The light's reflecting off the surfaces, bouncing around. That one, there's not really a name for it, it's just random. And then, were the voltage measurements changing between 3 seconds and a minute? Was there like a noticeable trend in that it would go down, stay the same, go up? And why or why not? And that sort of leads us to question 4, which is, what is a thermistor? So does anyone here know what a thermistor is? Yeah, so it's a thermal resistor. It's a resistor that changes its resistance in response to changing in temperature. So some of them increase resistance with an increase in temperature. Some of them increase resistance with a decrease in temperature. So for this one, you might want to talk about what kind we have. Does it increase or decrease with an increase in temperature? A little general maybe on how thermistors work, and specifically why we see maybe a reaction to the thermistor from the halogen lamps versus from the other light sources. So that's question 4. 5 asks, why did we measure the voltage output by the EPS board? So why did we measure it directly from the EPS board versus always from the LED board? Any ideas? good baseline. When we measure from the EPS board, that's measuring sort of directly from the battery. It's not going through anything else. The EPS board really just gives us a good look at our battery. And then why did we repeat it with the LED module?
To figure out if like, power consumption or voltage difference using the LED board from just using the EPS module.
Yeah, exactly. So how did it change when we added more stuff onto it? Is basically what we're looking at. And then we can compare between the jumper and the on and off switch. So I think most of us noticed that we had quite a bit of a difference when we used the on and off switch versus when we used the jumper, when we had the full stack connected. So does anyone have an idea of why we might have had that?
Well, I guess what's a much shorter circuit that the jumper creates? It's kind of less resistance, so less voltage drop.
Yeah, so that'll be one part of it is, as you can see, our jumper just immediately creates that connection. For the on-off switch, it has to go through the ribbon we have a little bit of circuitry up here to our switch. So the switch, we have more components in the circuit, so that's going to be more resistance. Another thing to consider is when you turn it on using the jumper, you're just sort of feeding power directly to your power regulators. When you're using the on-off switch, you might actually be sort of turning the power regulators on. So that's something to consider as well. How those regulators might affect your voltage if they're working, if the regulators are working. Then question 6 asks to plot the power profile expected by a satellite in low Earth equatorial orbit. So for that, we're going to look at this chart here. We're going to plot for 2 orbits, and we're going to go in groups of orbits. And each orbit will be split half into day, half into eclipse. And then on our y-axis, we're going to have our power from 0 to our maximum voltage. And we're going to plot curves for our solar panel as well as for our battery. So in the daylight, what would our solar panel power output probably look like?
It depends on your power distribution, but it would seem just like the constant amount of voltage.
Yeah, so when we're in sunlight, we're going to be getting power from our solar panels in eclipse. Naturally, we would expect the opposite. We're probably not going to be getting any power. And that's if it's perfectly day in eclipse. If you want, you can kind of change up this model a bit. So in the real world scenario, would we expect the sunlight to be constant throughout the day? No. Yeah. So if you want in your chart, you can maybe sort of have a curve like that or so. You could Google and find out what an actual power curve looks like for a solar panel throughout the day, type deal. So that's for the solar panel. For our batteries, what would we expect our battery to look like at the beginning of the day?
Beginning of the day, it'd be pretty. Well, you have some discharge energy, so you would need to recharge it.
Yeah, so at the beginning of the day, our battery will have some amount of discharge. Throughout the day, the solar panels are going to charge that battery. And then once we hit night, ideally we would have a fully charged battery. So that's sort of our 2 points here. Connecting these points, again, based on sort of what we learned from this, are we going to expect a straight line? Would we expect maybe some sort of curved line? So you can decide on that what you think it would look like. And a good thing to look into also would be depth of discharge for those nickel metal hydride batteries. For a new rechargeable battery, generally you never want to fully discharge it. That can be pretty bad for the cycling of the battery and affect its life cycle. So you'll want to look at how much those batteries will typically discharge to preserve their life the best. So that's something to look into. And you'll just need to draw those 2 curves throughout the full 2 orbits. And then the last question is just to discuss the sources of error in all the measurements made during the procedure. from the video, when you watch them do the first part of the lab, if you can find one source of error in that, that'd be good for that part of the lab. For when it comes to the light sources, I'd expect probably like 4 or 5 different sources of error, and at least one source of error sort of for each of the 3 light sources. So at least one for the LED, one for the halogen, and one for the ambient lighting, and then 1 or 2 more, just random ones, could be for any of them. And so that will be it for discussion. And then when we come to conclusion, again, just report the key findings of the lab. So things like, which of the light sources was best, what we found for maybe our LED board versus our UPS board, just all your key findings, whatever you think are the important takeaways from the lab. As well, you'll need 2 sources of error and a recommendation to go for each of them. For the sources of error, you can take them straight from discussion 7 if you want. You should still restate them in your conclusion and also explain how it will affect the lab. For example, if you have an emergency light that's always on, that might affect one solar panel more than the other. So you can explain how that would affect your readings. And then you can come up with a way to solve that problem or to correct that error. So for example, you could cover the emergency light with a bag or something, block the light. And if you want, feel free to use that example for your lab report. It's an easy one, so I don't want to steal it from you. So with that should be everything that you need to know for the report. If you have any questions, feel free to ask them. And I'll be sticking around